Let's talk about one of the most fundamental rules in the entire universe. Seriously, it's a rule that governs everything from how a star explodes to how your own body works. It's called the first law of thermodynamics, and it all kicks off with a really simple question. No, really, think about it. You've got that warm mug in your hands, you get that jolt of energy from the caffeine, but once the coffee's gone, where does all that energy go? Does it, I don't know, just poof out of existence? Well, the answer is actually pretty mind-blowing in its simplicity. That energy doesn't go anywhere. It just changes. It becomes the heat your body gives off. It becomes the kinetic energy you use to walk to your car. It even becomes the tiny electrical signals firing away in your brain. The one thing it never ever does is just disappear. So, this idea that energy is always changing forms but never ever getting lost isn't just some neat little thought experiment. Nope. It's a rock-solid, universal law. It's the core principle scientists call conservation. Here's the bottom line. If you could take a system, any collection of stuff, and totally seal it off from the rest of the universe, like put it in a perfect little box, the total amount of energy inside that box would never change. It could switch from chemical energy to heat to motion and back again, but the grand total, always the same. And of course, this unbreakable rule of energy accounting has an official name. It's one of the absolute pillars of physics. And there you have it, the first law of thermodynamics. This one sentence is so powerful, it basically says you can't get energy for free, no creating it out of thin air, and you can't just get rid of it either. The universe's energy budget is locked in. It's fixed.
Okay, so saying energy changes form is one thing, but scientists, they need to track it precisely. And to do that, they use their favorite language, mathematics. They've boiled this entire law down to one beautifully simple equation.
There it is. Delta U equals Q minus W. Now, I know what you might be thinking. Letters, symbols, looks a little intimidating, right? But I promise you, what this is saying is something we all understand intuitively. So to make this super clear, let's forget about physics for a second and think about something we all get, a bank account. Just picture the total energy in a system as the cash you've got in your bank account. All right, first up is delta U. That little triangle delta just means the change in something. So delta U is the change in the system's total energy. In our bank account analogy, this is just your new balance at the end of the day. It's the final results. Next, we've got Q. Q stands for heat. This is any energy you add to the system. So think of this like a deposit. You get your paycheck, you deposit it. You heat something up, you're making an energy deposit. And your total balance, the internal energy, it goes up. And finally, there's W, which stands for work. This is energy that leaves the system to go do something useful, like pushing a piston or lifting a weight. This is your withdrawal, your spending money. So the change in your balance, delta U, is just your deposits, Q, minus your withdrawals, W. That's it. That's all the fancy equation means. Now, to really see this law working perfectly, without a bunch of other messy stuff getting in the way, scientists love to study what's called a closed system. So what on earth is that? Well, a closed system is basically a container that doesn't let any actual stuff, any atoms or molecules, get in or out. But, and this is the important part, it can still trade energy with the outside world. It can get hotter or colder, for example. The coffee example is perfect for this. An open mug of coffee, that's an open system. It loses energy as heat, sure, but it also loses matter as steam evaporates into the air. But a perfectly sealed, high-tech thermos, it'll still get cold eventually, it's losing energy, but no water can escape. That is a closed system, and it makes tracking the energy way easier. So the first law is, without a doubt, a huge deal. But it's not the whole story. It actually has some really important limitations, things that it just plain cannot tell us. For example, think about an ice cube in a glass of water. The first law says that the total energy is conserved, whether the ice cube melts and cools the drink, or if the water spontaneously freezes and makes the ice cube warmer. Both scenarios balance the energy books, but we know instinctively that only one of those things is ever going to happen. The law doesn't tell us why. It also doesn't say how fast things happen or why every energy transfer seems to be a little wasteful. And honestly, that's the absolute best way to think about it. The first law is like a perfect accountant. It tracks every single bit of energy, making sure nothing is ever lost. The books are always balanced. But it's not a fortune teller. It can't predict which way things are going to go.
Which leaves us with one last really big question, right? If energy is never destroyed, if it's always conserved, then why can't we build a machine that just runs forever? Why does everything eventually run down? Well, the answer to that lies in a whole other law.